Welcome to our video presentation of power consumption optimization for intravascular cytometry with NXGen port. Hello, everyone. My name is Kevin Luong, and with me are my team members, Christopher Shum and Jonathan Chang.
Chemo patients essentially suffer from low counts of white blood cells and run into a multitude of minor and major complications. These patients often have to cancel or delay their treatments due to the poor blood cell counts on their treatment days. Chemo port catheters haven't seen much innovation. NXGen port's goals are to take the product and add optical sensors to it to measure blood cells, enabling a smart chemo port catheter, which provides critical information to help clinicians understand and proactively manage changes and symptoms in a patient's health status between clinic visits, which thus improves cancer care. Current market solutions also lack consistent methods to measure blood cell counts frequently, which also affects the cohesiveness of a treatment plan. The prototype will run off its own battery. So the aspect of the project that our team at UCI is focused on is the battery life of the device. Thus, our project goal was to gather the power consumption data of different microcontrollers to determine the most power efficient device and understand how the processes being run on them would affect the power consumption and battery life of the catheter. The methods we'll test are capturing raw images on a microcontroller and transmitting them to a host device like a phone or a computer through Bluetooth low energy. The host device will then run a neural network which analyzes these images. We'll then compare the same process but compress the images on the microcontroller before transmitting them over to the host device. And lastly, we'll perform partial processing over the microcontroller and the host device. Without these methods, we'll measure the power consumption of the microcontrollers using a USB power meter to determine which board consumes the least amount of power. And thus, the data collected will help the future goal of developing a system-on module for the first prototype.
In order to compress efficiently, we used the Quite OK image algorithm. We previously were proposed other compression algorithms like the wavelet transforms. But the pros of Quite OK outweigh the other algorithms. It doesn't use a matrix multiplication for compression and it is lossless, meaning the data is preserved. The only downside is that it isn't able to compress as densely as other lossy algorithms. The setup of one of our controllers started with setting up the CPU and hooking up to the camera cache. Then it was loaded onto memory and encoded by the Quite OK algorithm. Then it is stored into memory and then gets serialized and sent to the featherboard. Then the PC will read and decode the compressed image. There are three different setups that we made for compression and different algorithms. It is on the Raspberry Pi on the left, the Arduino Nano in the middle, and the Maxim 70800 EV kit.
Now looking at the power curves for each controller, we ran a sequence of commands like image capture, compression, and Bluetooth transmission for around 60 seconds. One thing to note is that the Bluetooth power for the Maxim controller is high and comparable to the compression step because the Maxim lacks an onboard Bluetooth capabilities. For the Raspberry Pi, we ran the same sequence, but here you can see that the Bluetooth transmission is low compared to the compression and image capture. Though the problem with the Raspberry Pi is that the overall power is too large, ranging from 3,300 to 4,500 milliwatts. Lastly, looking at the power curve for the Arduino Nano, you can see that the overall power consumption is still around 0 to 2 milliwatts. Also, when performing functions like Wi-Fi and BLE, you can see that the power is still comparable to the bare minimum and sleep power values. We conclude that although the Maxim controller is optimized for neural networks, the lack of BLE capabilities limits it from being considered for the smart port catheter. Likewise, though the Raspberry Pi is optimized for flexibility, its massive consumption of power also eliminates it from consideration. Our ideal choice for a microcontroller to be miniaturized into a port catheter would be the Arduino Nano because of its low power consumption and usefulness of IoT. Even when this microcontroller, it would still take around 7 pacemaker batteries to power the device. In order to implement this catheter, we must include implantable wireless charging technology. We'd like to thank our sponsors for this project, NXGen Port, and the company liaisons, Nancy, Roseanne, Mohammed, and Kathy. We'd also like to thank the UCI School of Engineering, and lastly, our faculty advisor, Farzad. Thank you.